Next up in our Module 5.1 class notes in example 4, we start to actually discuss the content of the module, which is exponential functions. And I like to come at it this way, from this angle, where we think about exponential functions from their applications, because there are a lot of applications. I'd like to say especially in business, but certainly in the sciences as well. Lots of applications of exponential functions, my favorite being ones that we'll get to in a couple modules from here, where we talk about compound interest and then annuities and loans. So lots of applications coming up with exponential modeling. For now, let's just talk about how to identify an exponential function, not even do any math necessarily with an exponential function, but basically just the fact that there are two types. That's oversimplifying. There are two very basic types of growth that we look at, whether it's population growth or investment growth. Pick your application there, but two basic types of growth that we look at: linear growth. Linear growth represented by a linear function, where you experience the same amount of growth every unit of time. Every year or day or month or whatever your unit of time is, you experience the same amount of growth. And we'll see an example right here on this slide. Versus exponential growth, where you see an amount of growth per unit of time. You see an amount of growth that grows along with the actual amount of the quantity that you're looking at. So basically, the more base quantity you have, the more growth you'll see, and that's called relative growth. So a linear growth is an absolute growth. It's a constant growth. It's the same every time. Whereas an exponential growth, or an exponential decay, as we'll see in this module as well, but an exponential change is a relative change, usually expressed as a percentage change. You're changing by some percent of the current amount. Let's see how that applies here in these two examples. Identify which of the following represents an exponential function and which represents a linear function. The first one: after a membership cost of $10, the cost to purchase any audiobook from a certain company is $2.99. So you pay your $10 up front, and then every time you make a purchase, it's $2.99. For the next purchase, for the purchase after that, it's still $2.99. For the purchase after that, it's still $2.99. For the 100th purchase, still $2.99. Doesn't matter where you are along that timeline, the next purchase is always $2.99. And so this example represents a linear function because there's an absolute or constant change of $2.99 for each book purchased. Whereas the next bullet has us looking at a population of bacteria that increases by a factor of 1/8 every 24 hours. So we've got a certain number of bacteria right now, and we will have 1/8 more than that amount tomorrow. And then we'll have 1/8 more than that new amount the next day. And then we'll have 1/8 more than that new amount the next day. And so it depends on how many bacteria we have. As a simple numeric example here, if we had only 8 bacteria today, then 1/8 of 8 means we'll have 1 more than that tomorrow. We'll have 9 tomorrow. Or if we have 8 million bacteria today, then we'll have 1/8 more than that tomorrow. 1/8 of 8 million is 1,000,000, so we'll have 1,000,000 more than that. We'll have 9 million tomorrow. So that's big change, big difference. The more population you have to begin with, the more of a change you will experience by a factor or some percentage of that amount. Here's my written explanation there. This example represents an exponential function because the change each hour, each 24 hours, I apologize for that typo here. It shouldn't say each hour, it should say each here, 24 hours. We all make mistakes. Get over it. This example represents an exponential function because the change each 24 hours is relative to the current amount of bacteria. It's a percentage change, 1/8, which if we translate the fraction 1/8 to a percent, it's 12.5% growth per day, per 24-hour period. So a percentage change, or a relative amount, an amount that's relative to the current amount, that's what characterizes exponential growth or an exponential function.